Howdy, I'm Alec Espiritu.
I'm Aria Fair.
I'm Madeline Sedlacek.
And I'm Nathan Bell, and this is our presentation about preparing solutions and calibration curves. And we're Chem 119, section 673.
The definition of a calibration curve is a graphical tool that is used to determine the concentration of unknown substances or solutions. Chemists use this so that they can convert instrument readings into chemical concentrations, which is an essential function for quantitative analysis. A real-life example of this is blood glucose monitoring, which is when they use calibration curves to correlate the electrical signal from a glucose biosensor into actual blood glucose concentration levels.
So you might be asking yourself, what is conductivity and absorbance? Conductivity is the ability of a solution to conduct electricity, and this is very dependent on ions. What ion is when a chemical breaks down into its two ions, a positive cation and a negative anion. It has the ability to conduct electricity through a solution as electrons transfer. So essentially, what that means for us is that the more ions that you have, the more conductivity a solution will have. And so conductivity is very dependent on the presence of ions, and it is also therefore directly proportional to the concentration of these ions. Absorbance, on the other hand, is basically just the amount of light absorbed at a specific wavelength. And Beer-Lambert's law states that this is also directly dependent on the concentration of these ions in solution. And so the more of these ions that there are in solution that will absorb a specific wavelength of light, the more absorbance that the solution has. And that is also another way to measure the concentration of these solutes in solution. And so essentially both of these are just ways to figure out how much of a solute is in this solution.
We took our solutions with known concentrations and measured the absorbance. And then we plotted the absorbance on the y-axis and our known concentrations on the x-axis. This created a linear calibration curve, which we were able to use to figure out our unknown concentration of the juice. Our unknown concentration falls right here, as our measured absorbance is 260, and our calculated concentration is 9.69%. A very similar process was used to create this calibration curve. We took our known molar solution concentration and found the conductivity for each concentration. We plotted them against each other and created another calibration curve. For this one, our unknown fell right here, which with a conductivity of 4.325. We plugged this conductivity into the y for this equation, and we solved for our unknown concentration, which was 0.0320 moles.
To find the concentration of the cranberry juice and the salt of the unknown solution, we'll use the two trend lines we found from our graphs. The first one, to find the percentage of cranberry juice, we'll plug in our calculated absorbance value we found in lab, which was 0.260, and plug that in for y, and then solve for x. To do that, we add over the y-intercept, which is 0.03, and then divide by 0.03, which will give us a value of 9.68%. To find the concentration of salt, we'll do the same thing. Our calculated value for the concentration was 4,325. We'll subtract the y-intercept, which is 77, and then divide by 132,000, which will give us our calculated molarity value of 0.0320 molar.
Thanks and gig 'em!